One of my favorite nerds in history is Rene Descartes. Though his whole cogito ergo sum thing was inherently flawed, he was still a wonderful nerd. I believe most of you have read his Meditations. He wrote a book called Meditations for AP Euro. But if you haven't, you should definitely read the translation. I love his writing style because he writes almost as if he was writing in a diary. He's explaining his every idea along the way, and it's really easy to follow, and you can see his whole philosophical thought process on the paper. Anyway, one of Descartes' many contributions to mathematics was the Cartesian coordinate system. Do you ever do any activities in preschool where you had a drawing with a grid on it, and you had to either answer questions about the location of a certain object, like saying it's on this square in the grid, or you have to make a mirror image of the drawing or copy the drawing? The advantage of having the grid there is that it's easier to describe or figure out the location of different parts of the picture, which helps you either find stuff and copy stuff. And Descartes took this a bit further by using a continuous number line. So instead of just saying that this item is within this box, you could say the exact location of the item based on its number on the number line. The grid can go in both positive and negative directions, with the x-coordinate describing horizontal location and the y-coordinate describing vertical location. Every ordered set of two real numbers describes a location on the grid, and every location on the grid can be described as a certain pair of two real numbers. These two are different things. Just because every set of two real numbers describes a location on the grid doesn't mean that each location on the grid can be described as a certain pair of two real numbers. For example, I can have a mapping that says, for every pair of two real numbers, that means exactly this point on the grid. Then every pair of real numbers describes some point on the grid, but a lot of points on the grid don't have a mapping to a real number. So when you have both these things, that's known as a bijection or a one-to-one correspondence, because each one input maps to exactly one output, and each output maps to exactly one input. But how do we graph these points on the plane? Well, if we have a coordinate, say 4, -5, and we start at the point 0, 0, which is called the origin because we start there, and we move horizontally according to the first coordinate. This one says 4, so we'll move a distance of 4 to the right because it is positive. If it was negative, we would move to the left. So we move a distance of 4 from the origin. Then we look at the second coordinate and move that distance up. So the second coordinate here is -5. -5 units up is the same thing as 5 units down, so we end up down here. And this is our point. But I'm sure you've had lots of experience graphing things on Cartesian coordinates before. You even heard of this weird polar thing, and I'm sure much of this experience was a long, arduous process of graphing a slight variation on the same sort of line 50 times over, as if we were computers or machines. And all this time, you were probably told that Cartesian coordinates were fact, that this was the only way you could ever describe a point on a plane using numbers. But that's not true at all. I bet you could come up with your own way of describing points on a surface using numbers. That would be pretty cool to do, actually. Just take any surface and find some sort of way to map every single point on the surface to a set of numbers. Let me know if any of you come up with anything. You want to know who did come up with something? Well, lots of people. In fact, I'm sure for the Cartesian coordinates, Rene Descartes wasn't the only one who came up with these coordinates. American history started in Europe and tends to credit things to a lot of European men and name things after a lot of European men, even though there's usually no one true discoverer or one true inventor of most achievements or inventions. But anyway, it's a bit of a sidetrack. One idea of making coordinates that became pretty popular was this. You have two coordinates, and you start pretty much the same way that you started for the Cartesian coordinates. You move horizontally from the origin using the first one, but then, using the second one, you take that entire line segment and you turn it according to whatever angle the second number describes. Then the point that you marked on the horizontal axis is now at the location of your final is now at the location of your actual coordinate. But so that's how you plot points, but just plotting points is boring. I want to make pretty shapes. And first, I'm going to test a few simple cases to get an idea of what I'm doing. What happens if the first coordinate is... Actually, saying the first coordinate is going to get really boring and really long and really painful. So I'm going to call it r. What happens if r is a constant? Let's say we're trying to graph r equals 5. We take a line of length 5 and move it across all the angles. Whoa, we found a circle. That's pretty interesting. But what if the second coordinate? I'll call the second coordinate theta because we're measuring angles, and mathematicians like using Greek letters to stand for angles. It doesn't have to be that way. It just mathematicians like doing it, and it makes things easier to read if you generally have one sort of symbol standing for one sort of thing. So what if we make theta constant? Theta some number. So let's say theta equals pi over 4, which is 45 degrees if you're working in degrees. Then we take lines of every single length and move it to this angle, pi over 4. Then we just have a line. So that's pretty cool. I'm pretty sure we could make every single straight line that passes through the origin just by making the angle different. But can you prove this? Can you show how to map a straight line in Cartesian coordinates to a straight line in polar coordinates? I'll let you try that out on your own. And I'm going to move on to experimenting with more shapes. So now we have two shapes we can make by holding things constant. What if we make both the variables same? So we have the equation r equals theta. This means the length will slowly increase when theta increases. If we plot only positive angles, we get a spiral. That's pretty cool. But then if we plot both positive and negative, then the radius starts becoming negative when the angle becomes negative, and that gets us this weird loop thingy. That looks kind of cool too. I wonder what happens if we plot r equals 5 theta, or r equals 2 theta plus 1, or maybe theta equals r plus 5. I bet they would look interesting too. But drawing circles and angles kind of reminds me of trig. So let's try some trig functions. We can draw r equals sine theta, and that gives us this cool circle up here. But let's try to see why it happens. Well, when we're over here, the sign is 1. But when we go down here, the sign slowly decreases until it reaches 0, and the same thing happens on the other side. And when we continue plotting, the circle repeats, which makes sense because the sine function is periodic. Or does it make sense? Does the period of the circle match the period of the sine function? If it doesn't, can you find a better explanation for this? A similar thing happens when we graph r equals the cosine of theta, where the circle is on the horizontal axis instead. I don't think I'm supposed to call them axes anymore, since we're not using them as axes, but anyway, it sits on this horizontal line, and that forms a circle that touches the origin and sits right here. What if we want to move the circle around? We can try adding stuff to the radius, say r equals bow tie plus cosine theta. But if we try this, we notice that this little bump forms. And as bow tie gets bigger, the bump gets bigger and eventually turns into a loop. I'm pretty sure I could come up with an algebraic explanation for this, but are you guys really interested in an algebraic explanation? Would it really explain to you why this happens? I don't think it would, but maybe an algebraic explanation is what helps you. If so, you can always Google it, and I will try to find some resources that have an algebraic proof for why this happens in the description below or like in a link attached somewhere. But anyway, I'm going to sort of model this using a nice little string that I have cut into a circle. So this is going to be our r equals sine theta graph. Now notice that when I pinch these two ends together, when I add a constant, I'm going to start pinching these two ends together. And notice this starts to form a little bump. The bump gets bigger and bigger and eventually gets too big and it forms a loop. Now, I'm not sure why adding some number would make this circle pinch together. If you can figure this out, please let me know. But otherwise, it would be a good question to think about. When we're modeling this in real life, this looks pretty much like a real life model of our graph. Why does it work like this? Why does our circle bend in this way? After all, you may use algebra to prove things, but that doesn't necessarily mean you need to use math to understand mathematical things. It's often nicer, especially in geometric problems, to find a nice visualization of why a certain thing occurs the way it does. And one thing that reminds me of is that when the circle is here, r equals 1 plus cosine theta, it's called a cardioid because it looks kind of like a heart shape. And I remember in elementary and middle school, a lot of people would have these doodles. I don't remember what they're called. I'll try to find a name, but I don't remember what they're called. But they drew a bunch of straight lines in certain angles according to certain rules, and eventually the final drawing would look kind of like a heart with a curve, even though all their component parts are straight lines. Clearly, I don't know what this was called, but if you remember drawing this or if you know its name, please let me know. And if you also know why your drawing worked by forming a curve with a bunch of straight lines and how that could be related to this curve, forming a cardioid, or if you have any ideas about that, again, let me know. Or if you have any sources that I could look at, that would be nice. Anyway, so I know this video was full of a bunch of questions and a bunch of I don't knows. My goal with this video was not to give you a bunch of rules for how graphing forms different shapes, because really, do you want a bunch of rules? That's kind of boring. What I would like for you, what I hope that you have gained out of this video is some idea of like, oh wow, I can draw cool things and I can try I can just play around with numbers and try get all these pretty shapes. And I highly recommend that you go on Desmos or some sort of graphing calculator and just spend some time to play around with these polar graphs. And the best way to become comfortable with a new type of graphing or a new type of equation is really just to play around with it and see how it behaves and what different things you can do with it. And once you've seen it in action, once you've done it yourself instead of just following some rules, you'll be a lot more confident and a lot more clear in your understanding of how and why this works. So please go try that out, and I hope you found some question interesting in this video, and if you didn't, please still go try something. Please still go try playing around with polar graphs and see if you find an interesting question on your own. Or just have fun with it. And if you make anything cool or find the answer to any of my questions, please let me know. I would love to hear what you guys have found out. But for now, that's all. See you next time!